Welcome, ladies and gentlemen. My name is Brian McLogan, and in this video, we're going to work on how to set up 28 different types of word problems. Now, the type of word problems that we're going to be setting up will be for right triangle trigonometry, oblique triangles using the law of sines, law of cosines, parametric equations, as well as vectors. Now, we're actually not going to solve them because the reason why I created this worksheet was that for students could just practice setting up the problem so they can take the words and go ahead and create a picture and either create a triangle or create some sort of diagram to better understand the problem. Throughout our unit in applications of trigonometry, we're going to learn the steps to be able to solve the word problems, but this video and worksheet is really just designed to be able to extract the important information given to us, and therefore then we can solve it mathematically. So that's what I'm going to basically do, is just kind of work our way through. We're just going to sketch a picture and then we're just going to label the parts. All right. And again, this is going to cover word problems for right triangle trigonometry, law of sines, law of cosines, parametric equations, as well as vectors. So if you have already learned some of those, you could continue actually solving those if that is something that you would like to, or if that is something that you also need help on. So in the first one, it says just two forces of 50 and 30 pounds are acting on an object at 30 degrees and negative 45 degrees in standard form. So if you remember, kind of in standard form, we're just going to have an xy axis, right? And remember, standard form is going to be off the positive x-axis, right? And we have one that's going to be 30 degrees. So let's say there's that force. So we'll label that at 30 degrees. And it doesn't say, but I'm assuming typically it's going to be respectively. So that's going to be 50 pounds at 30 degrees. And then 30 pounds at negative 45 degrees. So we're just going to go 50 LBS, and therefore that is again going to be a force. So we'll just kind of represent that as a vector. And then we'll have another one at negative 45 degrees. And that one's just going to be a little bit shorter. You know, we don't need to be perfect as we'll learn a little bit more in there, but it does help to make sure we try to get these to scale as best as possible. So then that's going to be negative 45 degrees, and therefore that force is going to be 30 pounds. Okay, and that's it. So that's all we're going to kind of work on. Obviously, you can see there is a question at the end. So if you know what to do, you can go ahead and work on that. But for right now, I just want to practice setting up these equations. The next one says we have two observers on opposite sides of a lake. Locate a house. Observer A is 800 feet from the lake house. Oh, I guess that's on two sides I locate a house. Observer A is 800 feet from the lake house, where observer B is 1,500 feet from the lake house. What is the distance between the two observers? Okay, so let's just draw a lake here. Now, it doesn't say this home is on the lake, but let's assume that it is. So let's call this A, and this B, and let's call this house, lake house. Okay, so observer A to here is going to be 800 feet. Okay, and observer B to the lake house is going to be 1,500 feet. And again, I don't know if this is a right triangle or an oblique triangle. I'm just going to kind of draw a picture, and then I can always adjust it as I need. It says, what is the distance between the two observers if the angle between them is going to be 15 degrees? Okay. So yeah, I don't have any other information to assume that there's going to be a right triangle or anything else. So therefore, I will just leave it like this, and then I can go ahead and solve. Now, a lot of times when I draw the picture, what I also told students to do is a lot of times when you have a triangle, is just to kind of like extract that triangle. Okay, so now I can just use just the information here. And now I can go and use that to represent D. So D is going to be the value that we're going to be looking for. Okay, it says a ball is thrown in the air with the initial angle of 85 degrees with the ground and an initial velocity of 32 feet per second. Determine the component form of the vector that represents the initial velocity. So it looks like it's just being thrown at the ground. So that's going to be 85 degrees in the ground. That's going to be from standard form. So I'll kind of do something like this. Actually, it's going to be a little bit higher, won't it? So I'll vector a little bit like this. Okay, so we'll say that is going to be 85 degrees. And then this one is going to have a velocity. Is 32 feet per second. All right. Okay, and that's really all the information we have. We just know that the ball is being thrown up in that direction, and then we'll kind of go from there. The next one is you take a walk heading north for 7 miles. Then you turn west for another 10 miles, find the bearing and the distance back home. So whenever we have something with like bearings, like you're going north, west, east, whatever, you're going to want to create a compass heading. So the first one, so I'll have north, east, south, west. All right, so then it says you're walking north for 7 miles. So I'm just going to say something like this. All right, so I'll say 7 miles. Then you're going to turn due west, so we're going to create another compass heading. Okay, and then it says you're going to do that for 10 miles. And then it's asking you for the bearing and the distance back home. So we've got a lot of bearings going on here, right, as you can see. So let's go ahead and just redraw this triangle here. We can now, since we have our bearings, that's going to be like that. We can say that that's going to be 7. That's going to be 10. Now, the bearing is going to be from here to here, right? So to be able to find that bearing, though, let me draw it a little bit bigger. To be able to find that bearing, we're going to need to be able to figure out what theta is. And then also it's saying what the distance back home is. So therefore, we'll also need to use that. So therefore, we'll need to find that angle as well as that distance, as you can from there. But at least you can see kind of like the picture. You're walking 7 miles north, and then you're walking 10 miles to the west. And that go ahead and creates a 90-degree triangle. The next one says you pull a cart up a ramp with an angle of 30 degrees with the ground. So again, I'm going to draw the ground, and I'm going to say, all right, let's have a ramp. And that's going to be 30 degrees. With the ground, find the force of the vector in the terms I and j. So let's just go ahead and do a cart. Let's, I don't know, do something. You pull a cart. That's not what I wanted. So let's do a bad picture. But there's the cart, okay? And you're pulling it. So that's going to be basically your vector, right? So that's going to be your force that you're going to be pulling it with. So therefore, we just want to be able to identify the force in the terms of I and j. But at least from now, we can just kind of see what it would look like pulling it up the ramp. The next one says an air balloon is lifted into the air by 2 ropes held in the ground, is lifted into the air by 2 ropes held into the ground by stakes that are 300 meters apart. I think I did a really bad job writing that. But again, looks like we have a balloon. Okay, and looks like there's going to be 2 stakes. So we have a stake here, maybe a stake there. And they're 300 meters apart. So we have 300 meters apart. And I guess I should have actually said that. An air balloon is lifted into the air by 2 ropes. Okay, that's in between. I forgot to mention that. I'm sure I need to make sure I fix that. Did I add that in there? I'm just looking back at my original one. No, I just kind of already knew. So either way, so our angle here is going to be 48 degrees as well as 46 degrees. Okay, in between the 2 stakes. And then how high is the balloon in the air? So therefore, oops, let's do a right angle. So therefore, in this case, we're going to be looking for h. So if I can draw this straight line here, you can see that now that's going to create a right triangle. But again, we don't have enough information at this point to be able to use a right triangle. So it is kind of important. What I'm going to do is I'm just going to draw 2 triangles. I'm going to draw the big triangle, the oblique triangle. That's meters, right? Yeah. Let's forget just 300. So we'll do 48 degrees, and we'll do 46 degrees, okay? And then I'm also going to do a right triangle. And with the height, okay? So therefore, we can just kind of understand how we can use it. We don't have enough information there, so what we could do to find the missing side of the oblique triangle and then possibly use the right triangle. All right, the next one says a plane travels from an airport at a bearing of south 40 degrees east for 30 minutes. So again, the important thing to look about this is that we have a bearing. So let's go ahead and draw our compass heading. So that's going to be north. All right, so north, east, south, west. So we're going to go south 40 degrees east. So it's going to look something like that. Okay, so that's south 40 degrees east. So you're going to do that for 30 minutes, and then you're going to do north 30 degrees east. So then the plane changes direction. So I'm going to create a new compass heading. Actually go down a little bit farther. Okay. Then it's going to go ahead and change. Oh, come on. I guess I can use, whatever, that's fine. This is not fun to, there you go. All right, I'll go with that. So now, so it travels through this way. Now again, we don't know how far it's gone, right? We just know it's been traveling for 30 minutes. And then at 180 degrees or 180 miles per hour. So therefore, that is going to change distance to north 30 degrees east. So we're going to north 30 degrees east. So that's going to look something like that. Now again, I don't know if it's going to go any farther. It looks like that's shorter, so I'm going to stop that right there. And then it says, what is the bearing to the airplane as well as the distance traveled from the airport? So it'd be, so therefore we're going to look for that distance as well as that distance. Okay. All right. So we got that, and then that's going to be 30 degrees. Now, oh, no, that's distance from the airport, not travel, distance from the airport. So we'll call that D. That's going to be our missing side. Now again, let's kind of figure out what our measurements here are. So if I do 180 miles for 30 minutes, right, that's that's going to be 180 miles per hour, right? So therefore, if you multiply 30 minutes is half of an hour, so that would be 90 miles per hour. So therefore, this one is going to be 90 miles, sorry. And then, let me just check, so 1/5 of 180, or 0.2, is going to be 36. So then here is going to be 36. Again, all I did is did 180 times 30 over 60 minutes, right? And that gave me 90. And then you could also do 180 times 20 over 60. And that is going to be my distance equals rate times time. So that's what I'm doing. I'm doing the rate, which is 100 miles per hour, times the time. So therefore, you could write them in decimals, but you can see it's over 30 minutes out of 60, 20 minutes out of 60. And therefore, that gives me 36 miles. Okay, so I didn't include a unit, but hopefully you can kind of see. And let's just kind of draw this triangle one more time here. All right, so there's going to be D, 90, and 36. And then you'd have to do a little bit more work to be able to solve from there. Okay, the next one says a surveyor determines the angle of elevation to the top of the mountain to be 28 degrees. The surveyor then, well, actually, no, hold on. I'm not going to solve it, but let's see if I could figure out. I could actually figure out the rest of this because that's going to be 40, so that'd be 70. I'll just figure that in, right? Because if that's 30, then that's 7 degrees. I don't know why I'm solving that, but I guess I'll just help you out so then you can kind of now determine what to do. All right, a surveyor determines the angle of elevation to the top of the mountain to be 28 degrees. So, okay, let's go ahead and have a surveyor. Let's go ahead and have a mountain. So, the top of the mountain is going to be 28 degrees, right? And that's an angle of elevation. Remember, angle of elevation is going to be an angle above a horizontal. Then the surveyor moves back 1,750 meters and records the angle of elevation to be 17 degrees and 30 seconds. So now we're going to move back. Again, I know my triangle is not that great, so that's going to be now 1750. Oops, I'm sorry, not that. That is going to be 17 degrees 30 seconds. Okay, and then that is going to be 750 meters. Determine the height of the mountain. So therefore, basically what we're looking for is this, which is going to be our h. Okay, so that's what we're going to be looking for is the h from there. So let's go ahead and just kind of draw this again one more time. Just a little bit better picture without all the fluff here. So that's going to be a right triangle. We have h. And then we're going to have basically kind of two triangles inside of that, which will probably be easier to draw them separately when you go ahead and solve and you write your equations. But for right now, we'll just kind of keep it as that. So you can kind of at least see what information, and again, this is going to be 750 meters. And then I would recommend writing this to be the distance that you were originally away from there. So that would probably be a helpful variable to use. All right, there are 3 marinas located on the water's edge that make up a right triangle where Marina A and B are perpendicular to Marina C. Okay, so again, we're going to have a nice little water here. So A and B are perpendicular. So here's C, so we'll have A and B. Okay, so the distance from Marina CB is going to be 130. And the CA is going to be 140. And then find the distance from A to B. Okay, well that's going to be fairly simple. Obviously just going to be Pythagorean theorem, but let's go ahead and draw this again out. Okay, so we have A, B, C, right triangle, we have 140, and then we have 130, and then we want to be able to find AB. So that's going to be that length, that distance right there. So then we have a right triangle, so therefore we can use our Pythagorean theorem, or Pythagorean theorem. All right, the next one is you could use your trigonometric equations actually as well. So you're standing 120 feet from the base of a bungee jumping platform. The angle of elevation from your location to the top of the platform where your friend is about to jump is 57 degrees. What is the height from which your friend is jumping? All right, so you're standing 120 feet from the base of a bungee jumping platform. So we're going to go 120 feet to the base of a platform. Okay? Angle of elevation from your location to the top of the platform is 57 degrees. We can assume that's going to be a right angle. Jumping, what is the height from which your friend is jumping? So, okay, so I'm assuming like here's the platform, so therefore that's going to be our h. Okay, so therefore we can see that we're just use a right triangle trigonometry to go and solve this one. The next one says a plane's head is on a bearing of north 43 degrees east at 490 miles per hour. Express the velocity of the plane as a vector, assuming there is no wind. Okay, so this is just going to be a very simple vector here. So again, we just need to create a bearing, nice little compass setting, north, east, southwest. We're just going to go north 43 degrees east. Right, and then now we can say that's going to be 490 miles per hour. The next one says a ship detects a shipwreck is 10,000 feet from the ship. The angle of depression from the ocean surface to the shipwreck is 35 degrees. How deep is the shipwreck? So we have a ship, right? And so we have water. And then we have a shipwreck. So let's do another ship. So we have a distance here from the ship to the shipwreck is going to be 10,000 feet. The angle of depression from the open surface to the shipwreck is 35 degrees. And I forgot to use my math notation there. So that's going to be 35 degrees. How deep is this shipwreck? So we're going to be looking for depth. We can use a right angle here, and therefore now use our trigonometric relationships. The next one says a boat is heading due north at 25 miles per hour and the flow of current is south 53 degrees east. Find the actual bearing and shape of the boat. Okay, so we have a boat heading due north. So due north. Gotcha. Okay, and that's going to be happening at 25 miles per hour. Then we have a current that is being flown at south 50 degrees east. Find the actual bearing and speed of the ship, but we don't know what that is. I believe that was 5 miles per hour. So we'll do south. Now that's going to be going 50 degrees east. So maybe I'll do something probably like that. And so that's going to be south 50 degrees. That's going to be 50 degrees, and that's going to be at 5 miles per hour. All right, the next one, number 14, says a camera at ground level is recording the liftoff of a rocket 900 feet away. Find the angle of elevation from the camera to the bottom of the rocket after it has traveled 2,000 meters in the sky. So we have a camera. It's going to follow a rocket. It's 900 meters away. So, here's the rocket. Right? And beautiful. Find the angle of elevation of the rocket to the camera to the bottom of the rocket after it has traveled 2,000 meters in the sky. So therefore, here we go. So 2,000 meters, and we want to find what is the angle of elevation? Okay. So we're going to be looking for our theta. The next one. Now we're past halfway now. Cool. So a captain on a boat wants to head directly east, but is facing a current of 25 miles per hour. Facing a current of 25 miles per hour at north 45 degrees west. Okay. All right, so there's a current at north 45 degrees west. That's heading here. So north 45 degrees. And that has a magnitude here of 25 miles per hour. But the captain wants to be continuous. He's traveling at 245 miles per hour, and he wants to be continuing in this direction. So that's going to be completely due east, and that's going to be at a vector of 245 miles per hour. So then basically what bearing should he be heading in? So what we're going to be looking for is, so let's do, not that one. What we're going to look for is this vector here. What is going to be that vector that is going to create that distance for us, or create that magnitude? So that is going to be our vector that we're going to be looking for. And actually, I should probably mention that. Well, in this case, you can see, yeah, that's what we're looking for is those sum. You don't really need to actually add that vector, but that's what we're looking for. All right, so this one says 2 cars are approaching an intersection. The first car A is 6 miles due west of the intersection, traveling east 40 miles per hour. And the second car B is 4 miles south due of the intersection, traveling north at 25 miles per hour. Using parametric equations, identify the formula for the distance between the 2 cars as a function of time. So if it says they're at an intersection, we're going to draw an intersection. I don't know why I'm having so much trouble drawing an intersection. There we go. Okay, so car A is 6 miles west. So let's just go here, and let's say, and that's approaching, right? So we'll just say that's going to be, at 6 miles here in the westerly direction, okay? And you could say like that's negative, right? Because it's going to the left, so we can say a -6, and then we can say that has a magnitude here of 40 miles per hour. The second car, B, is 4 miles south, so we can say like a -4. And that's going to be going up. So they're heading towards the same intersection, and that has 25 miles per hour. Okay? And then we're going to go ahead and use parametric equations from there. The next one says a point 100 feet in front of the library. The angles of elevation to the base of the flagpole And to the top of the flagpole are 20 degrees and 44 degrees, respectively. Find the height of the flagpole to the nearest foot. All right, so we have a flagpole. To the base of the flagpole and to the top of the flagpole are 20 degrees, 44. Okay, so oh, it's on top of the library. All right, so let's draw a library, first of all. And then we'll draw a flagpole. Okay, so we have a point 100 feet away from the front of the library. So we're going to say 100 feet. And we have two angles of elevation. So we have one that's going to be 20 degrees, which is going to be to the base. 20 degrees. And then we have another one, which is 44 degrees, which is going to be to the top, right? Because it makes sure that the larger angle is going to be, go to the top of the flagpole. And now what they're asking us is find the height. So we're going to find the h. So what might be helpful in this case is to draw two separate triangles here. So we could do, this is going to be 100. That'd be 20 degrees. And then we can draw, so that could be like height 1, because that's not the height of the flagpole. And actually, we just need to find the height, the height of the flagpole, okay. And then we could do, let me write this. Height, there we go. So then the next triangle, we could say that's still 100 feet, but now it's going to be 44 degrees, and we'll call that h2, right? So now we know that h is going to equal h2 minus h1. And now we just need to go ahead and use our trigonometry for right triangle trigonometry to be able to find our missing side. The next one says a plane flies 120 miles due north from the airport, then turns north 45 degrees west for another 100 miles. Determine the distance and bearing back to the airport. All right, so I have a compass sighting, so it's going to go 120 miles due north. Cool. So we say 120 miles. All right, and then it's going to turn north 45 degrees west. So I'm going to create another bearing, and then we're going to do that, and we're going to do that for another 100 miles. Then we want to be able to figure out the bearing as well as the distance back. So we'll say d, and then we're going to need to figure out the bearing. So let's kind of draw this triangle again because it's kind of small the way I drew it. So we have 120. We have 100. And we're going to be able to need to figure out this theta. So we do know this is 45 degrees. So that is helpful because if that's 45 degrees, then we know that is going to be 135 degrees. So we can say this angle is 135 degrees. So now what we need to find is determine the distance of bearing back to the airport. So we need to figure out this angle, so therefore we can go ahead and figure out the bearing, which is going to be difficult because not only that, you're also going to need to know that that angle right there is going to be 135. So if that's 135, if this is 135, then that's going to be 135, and then you'll just add whatever your bearing is to that angle. Okay, the next one is two airports are 150 miles apart. A plane needs to make an emergency landing for a sick passenger. Airport A detects the plane to be north 55 degrees east, while Station B detects the plane to be south 61 degrees east. How far is the plane from the airport A? Okay, so I'm just going to draw two airports. I don't know which direction I'm going, but I know that when I have bearings, I can go ahead and create a picture from there. So I'm just going to create two bearings, two airports. Now it says they're 150 miles apart. I don't know if one is north or south of the other one, but it doesn't really matter in this case. I just know that, okay, I'm just going to do 150 miles. So I'm going to say airport A detects the plane to be north 55 degrees east. So north 55 degrees east. So let's call this A then. So there's going to be an airplane. And the other one detects it to be south 61 degrees east. South 61 degrees east. So the main important thing is that you're going to have a triangle Now again, you could do these either way, but again, like I recognize if I'm doing north and south, then it only makes sense for my airplane here to be to the right, right? It doesn't make sense for it to be to the left or south or anything like that. So therefore, just by drawing those two bearings, you can kind of make sense and see how this triangle would be created. How far is the plane from airport A? So we want to be able to figure out, so we know this is 150 miles. And we want to, how far is the plane from airport A? So basically we would want to be able to figure out that distance. So what I'll do is I'll just kind of draw the triangle one more time. Okay, so we have this is going to be 55 degrees. We can say that is going to be 61 degrees. And then we're going to be looking for D, and we know that this is going to be 150 miles. So then from there, we can go ahead and solve using our information for oblique triangles. All right, the next problem says you throw a ball off a cliff 800 feet tall. So let's go ahead and draw a cliff. That's 800 feet tall. And you're going to throw a ball with an initial speed of 75 miles per hour at an angle of 45 degrees. So again, we need to create that angle of 45 degrees. Okay, so we're going to have a initial speed. So we're going to have an initial speed of 75 miles per hour. So v sub 0 is going to be 75 miles per hour at an angle of 45 degrees with the horizontal. Determine the, so that's going to be 45 degrees with the horizontal, okay. Determine the maximum height of the ball when the ball reaches the maximum height and how long the ball is in the air. So again, we're going to be using parametric equations, but all we have here is this initial velocity as well as an angle. And then we know that it's also going to be a height, so I should probably draw a triangle here. So we're going to make it say, okay, so we're looking for this, right? So that's going to be the max point. And then we're also looking for when the ball is going to be hitting the ground, which again, you know, t is going to equal 0, right? So that's going to be something that we're looking for. Not t is equal to 0. We're looking for what is the time, right? When the ball reaches the maximum height and how long the ball is in the air. Okay, so we're looking for the time when it hits the ball. So therefore your height, though, is going to be 0. So therefore that's what we'll be looking for our equations. All right, the next one says, an observer in a lighthouse 300 feet above the sea level observes two ships directly offshore. The ships of the depression to these ships are 8 degrees and 11 degrees respectively. Okay, so let's draw a lighthouse. So I don't know how to draw a lighthouse, but we'll... There we go, something like that. So then we have a lighthouse, and the angle of depression, so that's going to be 300 feet above the shore. Okay, and there's two ships directly offshore. So we have something offshore, right? And the angles of depression, now again, remember angles of depression are going to be angles below a horizontal. So we're going to say the horizontal is going to be like the eyesight from the lighthouse. So we have 8 degrees. And we have 11 degrees. Now again, remember this water level is going to also create a straight line here, okay? So we have, we're going to represent as 8 degrees, and then here we're going to represent as 11 degrees. So how far apart are the ships to the nearest foot? So we're looking for this distance, d1. However, we could, we're probably going to want to redraw these two triangles here. So I'm going to kind of draw this, because we can't really solve it as they're kind of written right now. So let's kind of rewrite them based on information, quality information that we have. All right, so if this is 8 degrees, so these are both right triangles, right? They're both 300 feet tall. All right, so what I'm going to do is I'm going to label this D1, and I'm going to label this D2. So the distance they are apart, not D1, the distance they are apart is going to be D2 minus D1. All right, now if this one's at 8 degrees, that means this angle here is going to be, the angle inside is going to be at 82 degrees, right? Because that has to add up to 90. So therefore, we're going to have another very, very small angle. And then if this one's 11 degrees, then we know that this one's going to be 79 degrees. Okay? So now you can see that we have two right triangles, and we can use our trigonometric ratios to find D1 and D2, and then we can go ahead and solve for D. All right, on to the next one. A 43-foot old cell phone tower is starting to lean to its side. Now, we don't know the side, so I'm just going to draw a little tower, or at least a line to represent a tower leaning. Let's lean to its side. From a distance of 133 feet from the angle of elevation to the top of the cell phone tower is 54 degrees. So it's going to be from a distance 133 feet from this tower. So 133 feet is the angle of elevation to the top of the cell phone tower is going to be 54 degrees. So again, remember, angle of elevation is an angle above a horizontal. We know that this is going to be 143 feet. And then we have 133 feet. How far is the tower leaning? Now, to answer the question, we basically need to be able to figure out like this angle. Well, to be able to figure out that angle, we're going to need to be able to figure out that angle, theta. So that is the angle we're going to be looking for. However, we're going to be wanting or use our oblique triangles to be able to solve for that theta. So therefore, we can actually figure out how far is the angle leaning, which is going to be, let's just call this alpha. All right, the next one is a plane. A plane maintains, I don't know. I'm losing it, I guess, doing so many of these problems. A plane maintains a constant speed of 510 miles per hour at a bearing of 315 degrees. The velocity of the wind is 75 miles per hour from the east. Find the actual speed and the direction of the airplane. All right, so now we have a bearing from due north. So let's go ahead and have 315 degrees is really just going to be 45 degrees west and north, but we'll just kind of go from there. So there's basically your bearing. So that represents 315 degrees. Remember, bearing is always going to be from due north. And then it says you have a velocity of the wind is going to be 75 degrees from the east. So we have wind that's approaching here. Now again, this plane is going 510 miles per hour. And then this wind is actually going 75 miles per hour. So really what we have here is this big vector here. And then we have this little vector over here. Well, not really little, it's still 75. But still, now what we're going to be doing is looking for that vector. That's what we call our resultant vector there. So that's going to be 510. So therefore, using the angles as well as using the magnitude, we'll go ahead and look into finding the resultant vector. All right, the next one is a boat is being pulled by a pulley at a dock that is 5 feet above the boat. So all right, so we have a dock, so let's just kind of create a dock here. So here's water. So we'll have a boat. And so that's going to be 5 feet. All right, so there's a dock 5 feet above the boat, or above the boat. All right, whatever. Given the length of the rope is 30 feet, so it's being pulled. So the length of the rope here is 30 feet. We can create this to be a right triangle because the dock we can assume is going to be vertical with the water. What is the angle of elevation from the boat to the pulley? So that means we're going to be looking for this angle. So what I'll do here is I'll just kind of draw a better picture. So then that's what I usually tell my students is, once you go ahead and, draw your picture, then go back and draw the triangle or the vectors or whatever may be the case. So therefore you can better understand. So therefore now we can just use our trigonometric relationships here to solve that. So this one, next one says a shadow is cast by the sun and a 50-foot building. If the angle of elevation of the sun above the horizon is 27 degrees, then find the length of the shadow. So we have a building. So we have the sun, right? So it's going to be casting a shadow here. So the angle of elevation of the shadow is 27 degrees. The building is going to be 50 feet tall, and we're going to be looking for this length of the shadow. So let's just kind of redraw a triangle here. So we can assume here that's going to be a right angle. We're going to be looking for the length of the shadow, right? We measure the length of the shadow as a horizontal distance. and therefore that'd be 27 degrees, and this is going to be 50. So now again, we can use our right triangle trigonometry to go ahead and find L. You throw a ball straight up in the sky with an initial velocity of 30 feet per second, with a height from a height of 10 feet. What is the maximum height the ball reaches, and how long is the ball in the air? So what we have here is we're just going to have a vertical distance. So we're basically starting, how long is the ball in the air? Okay, so hold on a second. Okay, so there's our horizontal distance, but we're not going anywhere horizontal distance, right? So we can say we're going to start at 10. And then basically this ball is just being thrown straight up in the air, all right? So we have 10 feet is the initial height, so we can say h of 0 is going to be 10 feet. And our initial velocity, v sub 0, is going to be 30 feet per second. All right, and then from here, we'll just use our parametric equations to be able to identify when the ball is going to hit the ground, as well as the maximum height of the ball. The next one, two observers are standing on the shore a half mile apart at points A and B and measure the bearing to a boat at a point C east of both points at the same time. So, all right, so we have a shore. So let's say A and B. They're on a shore. They're a half mile apart. So say 1/2 mile. The bearing to the boat from A is going to be 63 degrees. And the bearing from the boat B is going to be 56 degrees. So crap, I didn't really do that correctly. Because if we're doing 56 and 63, so let's do them a little bit lower here. Well, let's just put A down a little bit lower. So A has a bearing of 56 and C is going to have 63. Okay, so here, let's just draw. Why don't we just do A and then we'll do B from there. So if here's A, let me just erase everything. So you can see, like, I don't know what everything looks like. So what I'm going to do is I'm just going to say, all right, here's point A. I don't know if point B is above or below, but all I know is that point A has a bearing of 63 degrees. So I'm going to draw a bearing of 63 degrees, and then I'm going to kind of go from there. Right? So 63 degrees is going to be somewhere around there. And then we'll call this B point C. And then, so if I was doing an angle that's going to be a little bit less than that, right, then that's going to have to be below it. So I would say B, and then that angle, so again, that's a bearing of, this is going to be a bearing of 63 degrees, and then this is going to be a bearing of 56 degrees. And then we know that they are a half mile apart. So let's go and draw this triangle now. Again, one more time here. And then what is the distance from each observer to the sailboat? So therefore, we need to be able to figure out D1 as well as D2. So now we have this angle, 56 degrees, right? And that's 1/2. Here we're going to want to use complementary angles. So if we know that this is, I'm sorry, not complementary, supplementary angles. If I know this is 63, then I can figure out this angle to be 117 degrees. Okay, now we recognize this to be an oblique triangle, and so therefore now we can use the law of cosines to be able to solve for D1, D2. All right, no, I'm sorry, we can use the law of sines actually to solve for D1 and D2. All right, so for number 28, we're going to have a bridge supported by triangular braces. If the sides of each brace have lengths 63 feet, 46 feet, and 40 feet, find the measure of the angle opposite a 46-foot side. So what basically we have a bridge, right? And it's made out of triangles. So basically it says that one side is 40 foot, one side is 63 foot, and the other side is 46 feet. Okay, and they're looking for find the measure of the angle opposite of the 46-foot side, so that's going to be like our angle theta. Now, one thing I did not do, which I think will be helpful, is I'm just going to kind of tell you which type of problem each one of these are. So therefore you'd understand, I want to actually go back through all of the problems as we work our way back up just to make sure that we have the correct variables that we're going to be solving for, as well as understand what we will be doing here. So, or what we would be using. So in this case, we'll use the law of cosines. And you're looking for the angle theta, okay? Here we're going to be looking for D1 and D2. We can use the law of sines for this one. For the next one, we're going to want to use parametric equations. This one, the shadow, is going to be a right triangle. And we are going to be looking for L, which is going to be the length. The next one is another right triangle, so we'll just use right triangle trigonometry here. And we're going to be looking for theta, which is the angle of elevation. The next one is we're going to be looking for the speed and direction of the plane, but therefore that's really meaning the resultant vector. So that's going to be vectors. And R is what we're going to be looking for. In this case, we're going to be looking for the angle that the is leaning. We can use this is actually going to be the law of sines. Now, we're going to have to obviously solve theta to find alpha, but the final answer is going to be looking for alpha, which we're going to be needing to find. The next one, we're going to be looking for the distance. We have right triangles here. So I'll just say using right triangles. The next one is going to be using parametric equations. Obviously, there's going to be a lot of things we're going to be solving for. So I'll just write that as parametric. Parametric, that's a C there. All right, the next one is going to, we're going to be looking for D, how far is it apart from airport A? In this case, we can use the law of sines. Because we have two angles. This next one, we're going to be taking two different paths. We're going to want to use the law of cosines. So now what we're going to be doing is we need to be able to figure out basically this angle here. So we're going to need to find alpha, which is going to be the bearing, as well as D, which is going to be the distance. The next one is just going to be right triangles. And we're going to be finding the height. The next one is going to be parametric equations. Okay, and so we're going to be writing the parametric equations to identify the formula. The next one is what bearing should be the heading. So I'm actually just going to call that our resultant vector R. Okay, so therefore this one is going to be another vector problem. So we'll be using the, looking for R, the resultant vector, as well as the, what is it? It's got to do what bearing, and also the bearing too. So let's call that bearing, again, alpha. I'll just use alpha as my bearing. The next one, we have a right triangle, so we'll use right triangle trigonometry. And again, we'll be looking for the angle of elevation. The next one is, let's go and see, that's going to be find the actual bearing and speed of the boats. So therefore, again, this is going to be a bearing problem, or I'm sorry, a vector problem. So we have that, and so we have this from there. So we're basically looking for what is going to be this vector here. So a boat is heading due north in the flow of current, find the actual speed and bearing of the ship, of the boat. So actually we can do tilt ahead. So we have the boat going like this, and then we have a vector here. So we are looking for that vector, which is R. So that's going to be using, again, vectors. The next one is going to be right triangle. Oh, I'm like sharing the T. That's kind of an interesting way to write things. Didn't really mean to do that. So right triangle. Okay, a plane heads on the bearing north 43 degrees east. Express the velocity in the plane. Very good. So basically we're just looking for this vector. So just say, what is the vector form? So this is going to be using vectors. The next one is you're standing 120 feet from the base, angle of elevation. So that's going to be right triangles. This one is going to be 3 Marinas. We're looking for D. That's a right triangle. You're going to use Pythagorean theorem. Then this one is going to be right triangles. Now this one, you're actually finding the height, right? Determine the height of the mountain. Okay, so you're determining the height, but you're also going to have to determine this this measure, I believe. 1700, angle. Yeah, you need, oh no, you don't need to. You actually don't need to figure out that length. No, because what you can do is actually you can figure if that's 28 degrees, then you can use this. That's going to be complementary, so that'd be 152. There you go. So now you're going to have angle, side, angle. So no, you could use right triangles, I guess, maybe. Then you'd have to create an equation. That seems a little bit more difficult. So in this case, if you have angle and side, you're going to use the law of sines. Even better. All right, the next one is you're going to have, again, another side, angle, side. So in this one, you could actually use this to go ahead and use the law of cosines. And you're going to be finding D. The next one is going to be the law of sines, and you're going to be finding the height. So we'll use the law of sines. And we're also going to use right triangle trigonometry. So we're actually going to have two of them because you need to be able to figure out one of these sides. Okay, it doesn't matter which one you figure out, but you need to be able to figure out one of those sides to be able to solve for the height. Question number 5 says you pull a cart up a ramp 30 degrees, so find the force of the vector. So really we're just looking for what is the vector. Okay, so obviously that's going to be vectors. The next one is right triangle trigonometry. You're going to be looking for D. This one is going to be initial velocity. So we're just going to do a vector. So again, you can kind of see I already have the vector kind of set up. So let's look for V. It's going to be our vector. In this case, we have a side, angle, side. So therefore, we'll use the law of cosines. And then last one, question number 1 is again going to be vectors. So we're going to be looking for these resultant vectors. So we have this force. Let's say we're going to have, and let's say we have that force. So what we're looking for is going to be the resultant force. Now let's do something like that. So what we're going to be looking for is the resultant vector. So that's going to be vectors. So there you go, ladies and gentlemen. That is covering 28 different examples of setting up how to set up word problems for right triangle trigonometry, oblique triangles, parametric parametric equations, as well as vectors. I hope you enjoyed, and I look forward to seeing you on the next video. Cheers.